Okay, so let's get started with acid-base basics. These are the basic types of tools we need in order to do the more advanced problems that we're going to see. Okay, so we should know that water, okay, likes to self-ionize and will reach equilibrium with its proton concentration and its hydroxide. So water self-ionizes. This is H2O liquid. And you can also write it as two water molecules colliding. And when you do it this way, you'll get the H3O plus, called the hydronium ion, and the hydroxide ion. Okay, so what's happening here, as you've learned previously, in this first case, water breaks apart, and it's called the self-ionizing. Sometimes you'll hear auto-ionizing equation. In the second one, it's essentially the same thing, except one water molecule is donating a proton. And we learned in acid-base theory that this is a Bronsted-Lowry acid. And the one accepting is a Bronsted-Lowry base. Now there are three basic definitions. The first and the most easiest is Arrhenius, which we've heard about, okay, already. He had a very famous equation linking temperature and of course activation energy. Wow. Okay, with K, but he also was given the earliest definition of an acid. So an acid, by definition, or the earliest, was that, hey, acids produce H pluses, okay, bases somehow produce hydroxides, okay, and that was the earliest definition. Okay, I'll put AR here. Along came Bronsted-Lowry, and Bronsted-Lowry definition said, hey, to be an acid, I agree they produce H pluses in solution, but they do so because they donate protons, and bases, okay, accept protons. That's why I have the H2O, when it becomes H3O plus, does so because it accepts, and you should know why it can accept, because it's got a lone pair. Lone pair electrons drive a lot of the chemistry. That's why nitrogen, okay, is basic in organic chemistry, because of that lone pair. Okay, so in any case, we have one final definition, okay, and that's the Lewis, okay, definition. And Lewis is more encompassing. Let's go back to Bronsted-Lowry for a second. Bronsted-Lowry, okay, was more of a more encompassing definition that included chemicals that Arrhenius didn't feel were acids. Case in point, ammonia, NH3, is a base, but it doesn't have any hydroxides in the chemical, but we know when it reacts with water, it accepts a hydrogen, okay, and it makes the ammonium ion, which we've learned that's a lone pair coordinate covalent bond, and it produces the hydroxide indirectly. So it doesn't have a hydroxide, but it will produce it indirectly. Okay, that's why ammonium compounds. All right, now in the reverse, ammonium can give back the H+. But in any case, ammonia is an example of a compound that doesn't fit the definition. Now Lewis was even a more encompassing definition that included compounds that Arrhenius and Bronsted-Lowry did not. Okay, so Lewis definition included compounds that were acidic, but that weren't donating or accepting protons. And I'll give you an example in a second, but let's just write down its definition. So Lewis acids, okay, if you remember, they, okay, are lone pair electrons, acceptors. Whereas Lewis bases are, just like you said, lone pair of electron donators. Okay, and they're plenty of examples that happens in our chemistry besides that. The greatest example, I would say, is probably, okay, complex ions of metals. Copper plus 2 has a pH somewhere around 2. Very acidic. Yet it doesn't have any protons to make in a solution, as Arrhenius says. It doesn't donate an H, but somehow it makes it happen. How? Well, let me show you. Copper plus 2, let's go to another page here. Copper plus 2 has a pretty high charge density, pretty small, and what it will do is it'll attract 6 water molecules. And by attracting 6 water molecules, and you know, why 6, Mr. Grodsky? Well, 6 water molecules can fit around this copper. And I'm trying to draw 6 fitting, but I'm not sure if I'm doing a great job. But in any case, I'll draw one more. So 6 will fit in a octahedral pattern and make this compound, copper, H2O, 6, and the whole thing is plus 2. We call this a complex ion. We've learned about these in crystal field theory. Now, the coolest part about that is that because this charge density is so high, what it does is it pulls the pairs of electron in these polar covalent bonds closer to the copper ion. And what it does is exposes the positive proton that can escape. And this thing can give off a proton and become Cu H2O, now 5 OH minus 1. Now the whole thing becomes plus 1 because of the hydroxide we just produced. But that acts as a Lewis acid. Now, it does so because it's able to what? Accept a lone pair from the water's oxygen. Now, is it really creating a bond? That's controversial, but the bottom line is it's acting as a lone pair acceptor, and that can explain how metal ions can cause acidic solutions. Okay, now in easiest terms, how is a proton acidic? How is H3O plus acidic? We know when it reacts with a base, it makes water, but isn't this really accepting a lone pair? That's why it's also a Lewis acid. Now, this base, okay, is donating a lone pair. So it's really a better definition that will encompass all of the acids and bases that we'll see. So that's why Lewis acids include all of the definitions. Okay, enough of that. Let's get back to the equilibrium stuff that we started here. Okay, and let me erase this all. Now, continuing with our work here, let's take apart this top one and draw an equilibrium expression. So KEQ, law of mass action, is equal to the products over reactants. So my products are going to be H plus. I write a slash and write H3O plus to remind myself that these concentrations of the hydronium ion, the H3O plus, and the proton are synonymous. Whether I give you H3O plus or H plus, they are essentially the same thing in our discussions here on in. And of course, times a hydroxide. Notice I don't have any denominator here because this is a liquid. Solids and liquids do not apply here. Okay, so KQ is equal to the product of these ions, kind of like a KSP. Now, because this is a special reaction, okay, it happens in water, in aqueous solutions, we don't call this KQ, we call this KW. And at a fixed temperature, KW, remember it's equilibrium constants dependent upon temperature, is equal to 1 times 10 to the negative 14. Okay, so if I have pure water, nothing else mixed in, it makes sense that for every 1 water, 1 proton or hydronium and 1 hydroxide is produced. So I need 2 numbers, or I need a number, these are both X, right? Because it's a 1-to-1 relationship, I need a number that's the same when multiplied together gives me this number. And last year, remember that it was 1 times 10 to the negative 7. Just through stoichiometry, these concentrations have to be the same if the water is pure. There's no added influence of any other chemicals. So Kw, which is 1 times 10 to the negative 14, equals these values. Very simple stuff. Okay, so as we talked about before, no, I don't know what I just did here. Put that back over there. So let's continue. Now this, of course, is brackets. And that's, of course, my H+. All right, so what the heck is a pH, as we talked about before? Well, my pH is the negative log of my H+ or H3O+ concentration. It's a way of keeping track the log or the exponent of the actual concentration. We say, well, why do we need that? Well, we need that because there's a wide range of concentrations that can occur for water for these two ions. And these two ions drive a whole separate type of chemistry, acid-base chemistry, that occurs in water. A lot of our enzymes, most chemical reactions in water solutions are highly affected about the ratio of the proton to hydroxide availability. And reactions sometimes won't go at all, or will go very well, and our living organic chemistry really depends upon these ratios. So we need a way to easily try to quantify these small numbers and that are very, very different from each other as we add different chemicals. And the log base 10 of this H+ ion concentration is how we do it. So in any case, getting rid of this little negative log here, pH of 1 times 10 negative 7, if you put this in your calculator, is negative log of 7, and you can do this in your head, and I definitely applaud you to, want you to. This would be a pH equal to 7. Okay, and I just got that by doing the negative log. Okay, now I can also do the negative log of my hydroxide concentration. Don't leave him out of the mix. He, my friends, will be a POH. Not used as much, but we'll use it. POH is equal to 7. And of course, I really could also, if I wanted, and I want to, do the negative log of my Kw. And this would be 14. Take the log of this, take the exponent of base 10, and we make it a 14 times by negative 1, and it's a 14. So 14 equals 7. Okay, and let me get rid of these parentheses because they're not longer exponents. So Christmas in July. Okay, and 14 equals 7 plus 7. Or another way to write it is PKW, PKW, that's the negative log, equals pH plus POH. One very helpful, okay, equivalent. All right, the PKW, which is 14 always because we're going to be at a temperature that's constant, okay, is equal to the pH plus the POH. That'll be very helpful. Now, we can go back between the pH, these logs that help us to quantify these changes, backwards. We can go backwards a little bit. What's this? Okay. I can go back from my POH back to my actual concentration by something called the anti-log. I just call it 10 to the negative x. So you put this exponent back in here, 10 to the negative x, you get this number back. So anytime I give you a pH and you want to go back to the real concentration, it's 10 to the negative x, sometimes called the anti-log. I'm not really happy with that one. Just 10 to the negative x for me. And we've seen this before many of times. This would be 10 to the negative x as well. Okay, same idea. So to go back and forth is something we're going to do a lot of. It'll be very helpful. We need to understand that these values are read through meters And these are used for equilibrium. So when we're doing equilibrium or problems, we're going to need to be in molarity, and sometimes we're working back and forth in POH and pH. Okay, very, very helpful to understand that. And we have some problems in our homework that review that. Okay, before we get to doing some problems to review, we should clearly understand the differences in our strengths of acids. Now, when we have pure water, as I was trying to say over here, we have equal number of H pluses, synonymous with H3O plus, the hydronium ion, and hydroxide. And if they're equal numbers, they equal each other, the pH, of course, is going to be 7. Almost never do we have a pH of 7 in an environment. You have to have the pure water. So pH of 7, of course, that's our neutral, okay? That's our neutral pH, as we've talked about in many courses. Neutral because you have equal number of protons and hydroxides. Now, if you're less, if your pH drops, okay, a pH of, let's say, 3, well, you're going to have a greater amount, okay, and I should probably just write it this way, greater amount, your H plus, this is by H plus for now, we know it's synonymous with H3O plus, we have H plus is greater than my hydroxide, and if we have a pH that's greater than 7, so a pH of, let's say, 10, okay, we know that the H plus is less than hydroxide, and that's called a basic pH. Okay, something that we've been dealing with probably for a long time in many other courses. So this, of course, is our basic pH. Okay, anything above 7, and of course anything below 7 is our acidic pH, or acidic range. Okay, very basic stuff, but I want to make sure we're on the same page just by one little tiny easy type of problem here. And that is, if I was to give you a pH of, let's say, 3, like I said. Now, pH of 3 is easy math. That means the H plus ion concentration is equal to what? Well, it's 10 to the negative 3. We're going back from the pH to here. 10 is 1 times 10 to the negative 3. Easy. That means the hydroxide concentration, because it has to equal 1 times 10 negative 14, is, oh, you got it, 1 times 10 to negative 11. So you can get easy concentrations. Okay, the POH obviously is what? Yeah, 11. So you can see if the pH is 3, the POH would be 11 plus 3 is 14, is 11, and you can work backwards. Same idea. So very simple. Now, if you notice, if you compare these to, let's say, neutral pH, right here is the H plus here. I don't want to use that color. Here is my acidic pH, and here is my base, neutral pH. Notice this is an increase of H plus ions by about what, 4 orders of magnitude, okay, or what? 4 zeros. This is 10,000 times more acidic. 10 to the negative 3 is 10,000 times bigger than 10 to the negative 7. If you notice, this guy, compare the hydroxides differ by an order of magnitude about 10,000 as well, and this is 10,000 times smaller. So lower amount of hydroxides, and that's how all that works. I'm sure you get that. Okay. So at this point, what I'd like you to do is take out your acid and bases 1 pH props. I'd like you to work yourself through those problems where you're finding the pH and POH, and these are just the basic skills you have to have. And 1 through 6 will do you. I have the key to review, and I'm going to continue this discussion once you've done that, reviewed the key, and I'm going to go on to the next worksheet that talks about the strength of acids, which is related to Kas. And then we're going to get into some equilibrium problems, because we have to understand the difference between strong acids and weak acids, strong bases and weak bases. So we're going to get into a discussion of strong acids, okay, weak acids first, and of course the ability of an acid, this is just an arbitrary HA going to an H plus an A minus, depends upon how well it does this, goes in the forward direction, how spontaneous it goes. Well, we're not going to look at delta G's, but we're going to look at something linked to delta G's, and that's something called the KEQ of a reaction. Now, because they're acids, we call them KAs. How well does the acid dissociate? Well, if the Ka is large, that means there's more what? More products than reactants favored at equilibrium. I write the HA on the bottom because, okay, it'll be of some concentration. Okay, so if a large Ka means that I have a lot more of these ions, so therefore it's a stronger acid. In fact, strong acids have Kas that reach or approximate infinity because this number starts to approach 0 and these numbers have complete dissociation. So strong acids have Kas that are almost immeasurable because they're so big, but there's only a few of them to remember. Here is a chart that shows almost all of these strong acids, and you can see that the Kas are very, very large. HI, hydroiodic acid, hydrobromic acid, hydrochloric acid, okay, nitric acid, sulfuric acid are the top 5 here. But we actually have more than that, okay, and it's on the other page. Other side, okay, here are the ones perchloric, hydroiodic, hydrobromic, very large nitric. So these are the 1, 2, 3, 4, 5, okay, and this will be top 6, and we'll get more into this. Okay, so this list isn't all that comprehensive because it's missing the chloric acid, the perchloric acid, which is a chlorine and 4 O's. Okay, and it's also missing the chloric acid, ClO3. Okay, real quick on naming acids. If it's a chlorate, remember from your summer assignment, 8 becomes ic. Okay, and ite, which is the lower number, becomes ois. Okay, so these are 8. These are all 8s. This is an 8, so it's chloric acid. This is perchloric acid. Okay, and these guys are very strong. This guy would go in here somewhere. This guy is somewhere in here. I don't know for sure, but look at the Kas. They're very large. And this would be your top 1, 2, 3, 4, 5, 6, 7 acids that you should be able to recognize as acids that completely dissociate, which drive the Kas large. Okay, the coolest thing or the weird thing is there's no line in between. You're either strong and have complete dissociation, or you're a weak acid and you have barely dissociation. Look at these Kas. After being large, they drop off the face, which means that they are sincerely going to favor the reactant side if it's less than 1. So you either a strong acid, which is rare, or weak acid. Now the key here is that if you're a strong acid, okay, your conjugate base, which is the resulting compound that has no ability to go in reverse. This is very, very spontaneous in one direction. So these conjugate bases have no, and again, conjugate bases are what's left over after you've donated a proton, and they have no ability to go in the reverse. That's why they all have a tremendously high Kas. It's their conjugate bases have some ability to go in the reverse, and that's where you have weak acids, that the reverse reaction is favored and the Ka is less than 1. Delta G is negative. And as you can see, the Kas drop off as we go down, which means the conjugate base's strength increases. Okay, and we would say that the Ka decreases because the Kb increases. And we'll talk about that in tomorrow's lecture. But what I want you to get a handle upon is here's my conjugate acid, conjugate base, and they increase. The ability of the base to reassociate itself with the proton increases as the acid loses its strength, and we denote that strength or its ability to produce products or ions or protons by its size of its Ka. Now, if something is a weak acid, it's not going to completely dissociate. It's very important you understand this next point. If I'm a strong acid, the concentration of my acid will be the concentration of my protons. So the pH is easy. If I've got a strong acid and the concentration is 1 molar, well then let's make it 0.1 molar. Then that means that my 0.1 molar HI is going to make 0.1 molar H plus ions. And that's of course 1 times 10 to the negative 1. And my pH of course is 1. So easy problems if they're strong acids. If they're weak acids, down here, you cannot just do what we just did here. We can't assume complete dissociation, so therefore we need to do an equilibrium problem, minus x plus x, to figure that out. And you should be able to recognize that. Strong bases, okay, we'll talk about without a table. Okay, so strong bases are nothing more than salts of hydroxides. So, who are very soluble hydroxides? Well, remember your solubility rules. Hydroxides are notoriously insoluble, with the exception of group 1 ions, okay, and group 2 ions, but a selective group. We have our calcium, we have our barium, our strontium, I should say first, and our barium. So all of our group 1 ions, okay, are going to make hydroxide soluble as a salt, like sodium hydroxide completely dissociates into the ion. And of course calcium plus 2 will dissociate into 2 hydroxides when it is calcium hydroxide, and so would strontium and barium. But these guys are not quite as soluble. In fact, they're only strong acids in weak concentrations, and if you remember your KSPs, they have some value of KSP. Once you go past that, once Q, okay, is larger than K, then these guys don't work very well. So these guys are strong bases too, except they become insoluble at high concentrations. So these guys are strong bases but at low concentrations. So if you got a strong base, like hey, I got 0.1 molar NaOH, that means complete dissociation. So I have what? 1 times 10 to the negative 1 of my hydroxide, which is my POH to be 1, and POH plus pH equals 14, so my pH is 13. I can do that directly because I can assume that the concentration of my base is the concentration of my hydroxides. Can't do that if it's a weak base. Everything else is a weak base, and I have to use an equilibrium problem. Okay, what I'd like you to do now is do the second worksheet I assigned, and where you're going to notice that there's going to be some equilibrium problems. Don't forget, you're going to have to, when you get an opportunity to approximate sometimes. That minus x can be approximated if it's small enough compared to what you're adding. Okay, try that. I have the keys available.